Of course.
Okay, let's go back. Yep. So that is the formula for the inverse. That will be. Do you remember that? Do you remember that matrix? We put
yes,
we put a D here, A here,
yep,
negative B,
yep,
and negative C, and divide by and AD
determinant.
Take away determinant. That's right, and BC. Alternatively, you can written as that. So that's how the people write it. So that is we'll copy it again. So that is dA negative B negative C, right? That will be determinant. That's very important. The quantity is called determinant A. Determinant A. Okay. Just as determinant A, we know that is A, the determinant A. So by definition, determinant A, DET A, or can be written as this is different, slightly different notation. It's just represent, this is not a matrix, it just determine you are required to work out the determinant. Determinant just like it could be the area, okay? Graphically, it could be the volume or could it be the area. So that is A.
Would it be fair to say that the first part of the algorithm accounts for the reversal of the direction, and then the determinant accounts for the scaling?
Yes, it's right.
Reversal of the scaling.
Yes, that's right. That's right. The scaling. So this is the scaling factor because that will take into account of the not direction, but also the magnitude. Okay. So it's a combination. So it's determined by two. It determines that that scaling is the factor were determined by the both the vectors. That because they here involve two vectors, right? A, B, and C, D, two vectors. So therefore, after this inverse transformation, and one would expect that both magnitude will change. So that's how determinant was introduced to take that into account. Right. So of course, in this case, obviously, for so then go to the algebra theory, okay? But student found it boring because instead of go to practical side, they go to theoretical side. They say, well, they argue that, well, to have something in order to obtain inverse, and this determinant must be not equal to 0. Okay. Why? They want to save that, you want to avoid that catastrophe when the denominator becomes 0. Okay. All right. Yep. So that's a big deal. That's big in terms of theory. It's big deal. It's because it's whether a matrix is how to say inversible. Inversibility. So many fascinating terminology were used. Where is it divisible? And that depending on this condition. Okay, that's big deal. So have to, of course, we know that. That's because we know that if that is the case, then you will see the 0 here, right? Okay. So that's, you see from this point of view, it's the extension to the theoretical argument is trivial, right? But you know that's actually that's why I don't like mathematicians because they all of a sudden they go to the they're abstracting everything, they go to abstract, okay, and make the and the argument. But for students, I think it's important to understand that these conditions are natural, okay. Well, we could take it for granted, but if you want to do some course, you have to get familiar with this argument. That can you see. So first of all, you will say, well, what would happen? For example, let's go to example. This may help you to pass your linear algebra course, right? So if A equal to, I just make it happen like this, equal to 1, 2, okay, and then other side is also 1, 2, okay. So does that inverse exist?
No.
Why?
Zero determinant.
Yes, then you make argument because you make your argument because determinant. That's what teacher expect student to do. Okay, denominator is 1, 1, 1, 2, 2. That will equal to is 1 plus 1 multiply minus 1 plus 2 equal to 0. Therefore, no inverse exists, okay? Not exist.
Mm-hmm.
It's just example how to do the test, okay?
Sure.
Yeah, so I think that is the return to your query during our explanation. So basically, we have another example that's a common example. We have vectors, okay? We have vectors A, and we multiply the that is, we know that A will become the B, right? That's right. We don't have to draw the graph today. We know that would happen, that matrix represent the linear operation, which can change the direction of vectors as well as his length, okay? There's no guarantee that the length will be the same, but you will see that in a special case, you can. If you just rotate, okay? We're talking about that one. We talk about 90-degree rotation already, okay?
Yes.
Now, so if in general, this is that you will change that the opposed direction and the magnitude. So in this case, what can we, so the question is, how about B, okay? The vector, how about original vectors before the transformation? That is a big issue. That is the question you asked, right? In many cases, B is given. So given B is not given, so say just. So in many cases, many scenario, the B is given. B vector is given, is known, okay? So then you have to oblige to use our multiplication. We call it the right multiply. We have to, can we go to the left-hand side? So left means multiply matrix from left, okay? Multiply, and we just could be written more operational. So multiply inverse, okay? From the left, the left. Shall we say the left or from left? Just make English perfect.
Either.
Okay.
Both work.
Yeah, okay. So multiply that, and what would happen? What is unit try? That is how to solve this problem.
Yeah,
and
so
by in doing so, we speak linear algebra, not English.
Wait up, where's my pen? Sorry, 2 seconds. Pen on. A vector is equal to
Yep, that's it. Yeah, obviously you jump. Okay, you miss 1 mark if you go to test. You miss mark. You have to follow the children's what children was asked in the primary school. You see, you have to first of all perhaps just edit something here to make this argument sound. So basically you say, okay, let's do that. We follow that. So we got this one. Can you see? Not A, we multiply M. Sorry. A is vector in this case. We multiply M inverse, right? We just follow that instruction. And you have to do it on the both sides at the same time. So that's why we got inverse in front of the B. Okay? Then you say because M1 inverse, multiply M equal to unit, not unit. What do you call that? Identity. Identity makes, okay? Yep. Because that's a therefore, and therefore you got yours. Sorry, I can't tell you something unexpected. Okay. So therefore, so that's your argument. Can you see? Therefore, that's your argument. Can you see that's a little bit complete logic? Okay.
Yes.
I know. Yes. I know it's so simple, but you see, sometimes they can make story, too complicated by using, 3 by 3 or 4 by 4. Okay.
Yes.
It's the same. The idea is the same. I just say the same. Okay. So that is exactly why we need formula. So that is why we need a formula to solve for the given matrix. This is a general formula. Perhaps we'll take this chance to work out how do we just use this formula to solve that. So this is general formula, okay? So that's why perhaps next I give you, we can do some exercise. So this example 1, example 2, example 3. Let's just use this formula, okay, to see what's happened. So So say what is the matrix? So the matrix here. So we have say any matrix can be called C. C equal to. I put some number here. We put the 2, 1, 3, 1, negative 1, 2. Okay, can you find the inverse by use the formula?
Yes. As in using the formula
yeah,
here,
that's formula. Yeah,
up the
using
top.
formula. Yeah.
Yep. Sure. That would be C. Oops, C negative 1 equals 2, 3, 1, negative 1.
Yeah.
Divided by 3 by 2, take negative 1 by 1.
Good, good. Yeah.
Yep.
Okay.
Yep.
So what is factor? What is
Equal,
a, yeah.
Sorry, the factor is going to be 6 minus 6 plus 1 is 7.
Yep.
So it's going to be, yeah, 2, 1, negative 1, 3 over 7.
Yep. And to get the complete answer, you can distribute or expand into the vector that people expect you to do.
Oh,
you see that?
Yep.
So that's just
Yep.
like you factorize that 7. You put the factor, the common factor, back to each term, and that will give the perfect answer. Okay. Simple, right?
Yep.
That's it. So it's a big deal. We have done a lot of things. So perhaps today we can move to the eigenvalue. Do you agree?
Yes.
So what is eigenvalue? So exciting. Yeah, eigenvalue and vector. This is eigenvalue. Eigenvalue. And eigenvector. We talk about this at the same time because they're all related. Eigenvector. So we know that in general, we know that a matrix can make we can rotate or can transform a given vector to another. So basically M, the matrix, multiply, we just use the same notation here, will become the B, right? It's different vectors. Yep. But in special case, then we are lucky. If we are lucky, we will encounter something like this. A will equal to, say, the lambda, the constant, okay? A constant multiply A itself. So if I draw the graph, and that will help you to understand what is eigenvalue and what are the eigenvectors. So basically, in this case, if you have, this is just given set. Okay, this is a basis. We're choosing with the basis, and in this case, in this special case, you will see that the change. So you will see that. So the A is vector here. A is vector here. In a special case, you will see special case. The vector, the other vector, can we just use different colors? Can we use the red one? So basically, the B vectors. Normally, B vector could be anywhere. Can you see? Depending on what the M is. But in this special case, the B will be here. Can you see? Parallel.
Yes.
Either parallel or anti-parallel. It's called anti-parallel. You see. So in either case, can we just do this one? Can we just make sure this? Can we just do this opposite? Doesn't matter. It could be this called anti-parallel or parallel. In this case, you will see that they are on the same straight line. See, if you want to draw the straight line, they are straight lines. So in this case, in this particular case, the B equal to lambda A is parallel to A. Do you agree? parallel or anti-parallel, depend, okay, depend. So so basically if your lambda is a positive number, and that should be parallel. You see, we use the geometry again, okay? We're back to geometry.
Mm-hmm.
And if lambda is a negative number, that is anti-parallel.
Mm-hmm.
Anti-parallel. Of course, it's a special. How about lambda equal to 0? It's the same, okay? It's just on the same line. So on the same line. In both cases, they are all on the same line, right? On the same line, determined by A. So that is something very interesting. In other words, this transformation only changes the magnitude of that vectors, okay? So that is why, so therefore they have proper definition. So the definition comes, so the definition. So they have lambda, so basically, so if there's a lambda, so if you use lambda and the chemical, in general, can we use X as vector, the capital X. So lambda is used as called eigenvalue. This is called eigenvalue. That is definition, eigenvalue. And X, the vectors, is called eigenvectors. So how far have you gone in the past when you told me you haven't heard or you have used these two concepts?
I have heard of them. I have not gone very far. The only other thing the only other kind of intuition I would have is because they're easy to work with, eigenvalues and eigenvectors, the point of a transformation can be to find an eigenbasis to make things easier. That's right.
I think now we need to put all these relevant information together, okay? So basically we return, okay, these issues are related, right? Because you when we talk about the basis, and then we have to get oh, got a message from Zoom.
Just sorry, that's okay.
It's okay. About 10 minutes time, we can resume it, okay. So basically, what is the eigenvalue of M? So by definition, this is the equation you need to know. So basically, this is eigenvector, and that would be the eigenvalue. So this is more compact definition of what is eigenvalue or what is the eigenvectors. And the big issue, again, this is another big issue in algebra, linear algebra. So we are interested to determine that both the eigenvalue and eigenvectors. And what would happen, you will see something unexpected. I will to answer your question first before we journey start. In that particular representing, if you choose this eigenvalue, and the matrix will become diagonal. Can you see that? So basically, that is a key. That is an objective when we introduce this idea. So basically, at this moment, it appears it's just a mathematical issue, right? Eigenvalue, eigenvector. But in practice, when you're solving the problem, that will give you a very. So basically, you have to. We're talking about that if we have time. But probably today we just focus on how to determine these two quantity. So basically, what does this mean? So that implies that the n can be diagonalized. So basically, can we put we put the proper p here, another vector, another matrix, and that n can be transformed. Can you see? This notation is for the transformation of matrix, not vector. And that will become diagonal matrix. D for diagonal, D for diagonal, diagonal. So in other words, D is this is very handy because D is diagonal. If it's 2 by 2, so D is diagonal. Can you see that D is diagonal? So for example, I go to example. For example, 1 and -2. Can you see that? A diagonal matrix is much simpler than the matrix because the matrix got non-zero elements everywhere. However, for diagonal matrix, the non-zero only appear in these diagonal positions. So that's very important, see? So if you are looking for transformation, you probably will end up with very complicated, you know, the 2 by 2 or 3 by 3 or n by n. Then n by n, you got how many elements? N multiply n, right? So 2 by 2 is 4, 3 by 3 is 7. And oh, by the way, Einstein's formula for general relativity, they got 4 by 4 elements. So all by 4 by 4 elements, 4 by 4. So therefore, Einstein's equation, they only have one equation, but that implies there are 16 equations.
Okay.
You see that?
Yep.
So in both math and theoretical physics, people are trying to use more compact notation. Obviously, if you can diagonal Einstein's matrix, right, to diagonal, then the number was significantly reduced. Okay.
Right.
So number was significantly.
So it is a linear formula, though.
Einstein's equation.
Yes.
Well, it's good question. So Einstein formula, yeah, sometimes we can jump. So by Einstein's question like this, I can write it down here. So basically, got this matrix. So got R matrix. They use this is just Greek letters because mu and v. If you want, you can use I and J, okay, or you can use it's the same. So this Einstein question. So take away half, and this another matrix here. Another matrix here, and then multiply constant. Because I'm teaching another student, he asked me this question, so I can. So this question just come up from my head. Yeah. 80 pi, big deal. Einstein's contribution, creation. So this is I, 4 pi g. G is a constant for gravity, divided by c to power 4, and they got another matrix here. That is mu and v. So in both cases, mu were equal to 0, 1, 2, 3. And also another Greek vector is also changed to 0, 1, 2, 3. That is Einstein's equation in the matrix form.
I see.
Well, it looks like linear, but things getting very, very complicated because these elements are not linear. Okay, these elements are this called the curvature in the space-time. It's very abstract.
Okay, so this is relativity.
This is general relativity. This is called Einstein physics. This is called the big deal, Einstein. But you know how to deal with Einstein equation. Looks like this. Okay. Einstein's field equation.
I just watched Interstellar yesterday, so I've got relativity in my head.
Oh, good. Okay, yeah. Well, that's big talk. If you're interested, you can talk after this. Another way I can, if you wish, we can talk about my feedback about your recommended that idea to brain and how to use how brain works. Okay. I probably just give you just a brief remark. I think that is it sounds good, but actually that guy is dealing with machine learning because that method has been exactly applied to teach machine how to mimic the brain. Okay, in other words, for example, if you follow the constant transformation and you may miss out a big pictures, right? For example, for the pattern recognition, for example, if you face a shadow, you choose a circle. It could be the apple. It could be anything. But now eventually you work determine whether it's not apple or apple when they have the process. Okay, this process is continually learning process. So perhaps when you say the circle, probably immediately will depend on your preference. It could be the cookie, right? It could be anything, and not instead of apple. So how can machine rather eventually reach that conclusion? It is definitely not an apple, or it's definitely is apple. Then that is due to in between. After you can divide this process as many transformation. Okay, each transformation can be used a matrix. Do you agree?
Yes.
But that guy's idea is that unlike Markov metrics, they use constant metrics there, okay? And they just repeatedly use that matrix, assuming that each step is identical, transformation identical. Of course, that can work for some extent, but not necessary for machine learning, right? So therefore, his argument is that we must use the statistics in between each transformation, okay? After doing the transformation, we have some feedback from our existing knowledge or some reference so that we can refine or modify that previous transformation, make it more realistic. So that is how machine learning happens, in my opinion. So basically, the machine will constantly adjust that metrics. They don't have to use the same metrics. They use more refined metrics. And after a while, in another thing involved, they have to, that economy of time, or in terms of physics, it's called minimize, the minimize action or minimum action. So that will determine the path, how to reach that particular conclusion. But unfortunately, I can give you a general my response. This, personally, I believe this doesn't apply to the real human, you see. You can build the machine which behave into when you solve some how to say ordinary questions, or not necessarily question, could be the chess. Okay, play the game, predict the weather. It's not big. It's not easy question. It's very complicated compared with human intelligence now. But still, I think that is a machine learning curve. Okay. Now, what happened inside the human brain? I think, well, you can hardly say that it's simple as that. Okay. So it's some similarity. Okay. I'm interested in that. Sure. I want to learn more. And actually, yesterday I was watching another guy who is British. He firmly believes that every intelligence can be described by genes. Okay, so she actually associated each gene. So that is the origin. But personally, I think